All right, welcome back. So we're in week 9. Just few quick things before we start the presentation. So we're gonna have the exam this Wednesday. Hopefully, this is not the first time you hear about this. It's going to be in the class, about 90 minutes or so. I don't know the exact details. It's going to be open notes. So you're welcome to use your tablets or laptops. It's going to be on Gradescope. You can also write it down on a piece of paper if you really want to, and then take a picture. But you have to actually cannot do that. So you have to actually type it. So bring a laptop. If you can't really bring a laptop, then let me know. But I doubt that you will have a problem. Things that you are allowed and not allowed. Things that you are not allowed is searching the internet, using large language models or any sort of AI, and sharing your answers or chatting with anyone else, either like physically speaking or digitally speaking. But you're welcome to use other apps and notes and lectures and videos. You can do all that. So whatever you have in your computer and you want to use it, you can do it. There are books that you want to use, that's also fine. And of course, you will be connected to the internet because you need to type it on Gradescope, but I'm assuming that you're not going to use other tabs in your browsers, right? The exam, there are samples that is posted on the website if you go, or just click on this link. I put 3 samples, I think, for the last 3 years. One important thing is there are topics that we didn't cover this year compared to last year, and there are topics last year that we didn't do the previous years, and so on. So if you see a question and you have no idea what this question is about, hopefully, most likely means that the topic hasn't been covered. It doesn't mean that you have no idea, but you can double check as well. The best way to prepare is watching the lectures and looking at the videos and watching the videos. And then, as I said before, presentations also count and considered, including today's presentations. Papers themselves are not part of the exam, but again, you can have the papers handy if you have any questions. If we might ask any questions from that is relevant to a paper that's been presented, you can always look into the paper as well, but we're not going to directly ask questions from the paper that's not been covered in the presentations. If you're a CA student, I think we might have one. You can take the exam via Zoom from wherever you want. Just message me before so that we can communicate the logistics. If you're approved CA students, that send me a letter. I think I already got just one. Other people should be here in person. And then the type of questions that you're gonna see, similar to the samples. In some years, we had true or false questions and multi-choice questions coupled with some more short answer or long answer questions. In like a long time ago, we had like a very open-ended type of questions. My expectation is that we're gonna have a mixture of shorter questions and then longer questions, depending on how things are going. So you're gonna you should expect to see kind of style-wise would be fairly similar to previous years. Is there any questions about the exam? Good. All right. CA3 is about attestation. It's also on the website. The due date is next Monday. Next Saturday. Not this coming Saturday, the Saturday after. March 15th. Also on Gradescope. And then there is the final presentation, final project and final presentation. The sign-up form is there. I also posted on CampusWire. I think It was mostly full. Let's see. I think the first, the Wednesday one was full already. I cannot click on it for some reason. So the format of the presentation is fairly similar to your paper presentations, of course, but this is the different part is this is the material, the new material that you're covering. So try to address it by like what sort of problems you try to solve, and then explain what you did. I'm expecting some of you will run into issues that, oh, we tried these different things, none of them work kind of thing. That's fine. You can also explain those. Try to show the progress so that we see that you actually put in time and effort. Uh, and again, this is more of a research, and one thing that you will learn when you're doing more research is that most of the things you try will not work. So it's very, very natural that you try a bunch of different things and none of them worked. And then you run into many, many different issues. That's just the nature of research. And in real world, you will see that as well. So like, your class projects and all, they are nice and easy because they're like someone else tried different things and they all worked, and then you kind of just reproducing it. But for research, nobody has done it before. That's why it's new and novel. That's why we don't know whether it's going to work or not. So explain your failures as well. Don't just talk about what you have done. And then finally describe the outcomes. So it's like, design a code or design an experiment, what happened, and so on and so forth. The presentations, of course, will be in groups. You can decide who wants, it could be only one person presenting, it could be a group of you all presenting. It doesn't matter. So if someone is also not be able to make it and the others can present for themselves, that's fine. But make sure that you list all the names, especially for the report. If you're within your group, you run into issues such as, oh, someone didn't do anything and the others did all the work and kind of things like that, you can always message me and we can try to sort it out. Then in addition to the presentation, you also have to submit your report. Report has to be 4 pages. If you really need to add more things, you can have more pages. So it's like a soft limit. I ask you to have the IEEE transaction template. It's a LaTeX file that I also uploaded on the website. Try to use that. If you don't really want to use that and want to use the Word version of that, you can also Google it and you can find the Word version, but try to also use LaTeX because it's a little bit nicer. The due date for your report is the Friday of finals week. So essentially between your paper project presentation and report, if you have done everything and you're ready, you can just write the report and be done. But if there is like, new experiments that you need to do and things haven't really finished by the time that you're doing the presentation, just explain in the presentation what you have done so far and what you're planning to do in the next week. And then in the report, you have to basically deliver those things that you're going to say that you're going to do. That's also quite common because usually things happens at last minute, right? So week 10 magic happens, finals week, many things happens. So you can do that as well. So don't worry if you still there are things that you want to finish before you submitting the report. Your report is the final thing. So if you have some more experiments that you need to do, I might also give you some feedback of like try this or try that when you're giving the presentation. So that could be something that also goes to your report. Any questions? Yeah.
Slides for the presentation.
Yes, yeah, of course you have to come and present. What's that?
Is that
Online as in? No, you have to come here and present it, right? So there is a sign up form, there are time slots. Just put your name, so it's an 8-minute slot. And then it's similar to the paper presentations, yeah. So at least one of you should be here and present.
Is there any feedback we get from our peers on the project?
For the projects, yeah, I'm gonna give you some, I'm gonna ask you some questions while you're presenting.
Oh, no, the form that we did for.
Oh, students' feedback? Probably not. I mean, we can try to just optional option. We can provide that. You already gave feedback for the presentations, but yeah, I can do it as an option. Whoever wants to do it, yeah. And then I can share it with the presenters. Any other questions? One last thing is Wednesday Wednesday slot. We need one slot because one group they cannot present it on Monday. Is there anyone who's willing to give up their Wednesday slot and move themselves to the Monday? No one. So okay. Think about it. If anyone is willing to give up their slots and move to Monday, let me don't move yourself because if you move, then someone will grab it. But please message me so I can move the other groups there. But yeah, it's very precious 2 days. I know. All right. Any other questions? And then in terms of, as I said, we talked about the exam, so it will be everything, including all the modules, right? And the paper presentations, including today. And then the best way to prepare, as I said, watching lectures. If you have questions, post it on Campus Fire first. That's the easiest way for all of us to answer. This also helps others to see the questions. But I'll be available tomorrow as well in my office if anyone wants to meet in person and chat. Unfortunately, tonight I have to leave right after the class for a meeting. But tomorrow most of the day I'll be in my office. So you can just feel free to drop by or just message me and then we can find the time. Okay. Wednesday morning also should work. I'll be around. Okay. Awesome. So who's the first group who's going to present today? All right, so
Okay,
Hi, we're group 4.1, and we will be presenting on ARI, Attestation of Real-Time Mission Execution Integrity. I'm Joseph.
I'm Lauren. Okay,
So we have a smart car here and just driving down the road, and it's got to have some sensors to detect any obstacles in the way. Like, and we know this lidars are susceptible to attacks, and we know this from group 1.1. So let's say we run attestation on the car, say once every 5 minutes, to see if an attacker has infiltrated the system. Because like this guy here, we all like our cars virus-free, right? But suppose we were taking so much time with attestation that by the time we detected a pedestrian in the way of the car, and we verified that this car is not under attack, it's 5 seconds too late, and boom, we hit a kid. This car is an example of an autonomous cyber-physical system that operates independently without human intervention and performs real-time tasks. And with real-time tasks, real-time tasks must be completed before the deadline. And otherwise, it's game over. So what kind of attacks can the attacker make here? Let's think about the threat model. The first that comes to mind is a latency attack, in which the attacker creates a resource contention, such as cache pollution, to waste our time and basically make us miss the deadline. And another attack that comes to mind is a jitter attack, in which the attacker introduces some unpredictable timing variations into the task execution. And finally, I can think of a butterfly attack, in which the attacker changes some GPS signals to create flaws in the timing of our tasks. So here are the two main takeaways from our paper. We basically want attestation, but it has to be real time, and it has to be over the entire mission, meaning continuous attestation. And in doing so, we want to measure code integrity, data flow integrity, and control flow integrity. But the main problem here is that the overhead is too big unless we make some changes. The goal here overall is attestation of real-time mission execution integrity, RMEI. But why is continuous attestation of mission integrity that part of RMEI so important? Well, let's think back to module 8, where we learned about top 2, time of check to time of use. Basically, the idea is that when we're not attesting, we don't know if our system is compromised. So if we're driving down the road and say a malicious attack happens later on, then we don't know what's gonna happen. We might literally hit a car. We might literally hit a kid. Okay, fine. So we want continuous attestation. Fine. But the overhead's gonna be too big, right? And remember how professor said in class that if we're just attesting all the time, we may as well not have a device that works. So let's think back to module 7 where we learned about basic blocks. What if we could somehow divide the software into tiny blocks that are isolated and somehow distinguish which ones are more critical to the operation than others and focus on those for attestation?
All right, so let's go into our solution overview.
There's microphones.
Oh, yeah. Right, so let's get into.
You can put the microphone
Yeah.
there.
That's what I'll do here. All right, so let's get into the solution overview. So obviously we want to.
hold.
Oh, okay. We want to basically verify what are the properties of like these CPS systems, your drone, your smart car, whatever, that we want to like verify to make sure it's like secure. So a secure CPS software would have certain attributes such as normal code integrity, CFI, so code flow and integrity, DFI. But something that's kind of unique with these systems is that we also want to verify the timing, right? As Joseph just mentioned, like if your car senses that there's a kid in front of you, you're going to hit the kid, and that's going to be a big problem. Now, the problem is with verifying these things is that we can't verify everything. We have an issue versus where we have to make a trade-off between scalability and the actual security of the software. So our solution is we only attest exactly what's needed. And we'll go into exactly how that happens. So compartmentalization. So you can think of, our source code. Let's say this first like red box is let's say the software to like drop a bomb, and then maybe our second blue box is like the software for like IO processing. So obviously these don't have the same criticality, right? The bomb dropping is very severe, so we're going to call that critical compartment, and the IO processing maybe we label that as a less critical compartment. And we execute this via software fault isolation. And this is done by the compiler. And the compiler also is able to add instrumentation so that it can verify CFI and DFI as well. So how do we do this more performantly, right? So obviously we can't be logging every single event, every single, like assembly event. So what we do is we only check on log entry and exit times between compartments. So you can see that between like a blue box and a red box, so a non-critical and critical compartment, we check when did we enter and when did we exit. So this way we only have to check the timing of those between those like indirect jumps. Then within critical compartments, we obviously want to have more fine-grained like security checks. So what we do is we also check the timing and we log like indirect jumps within those critical compartments. And so we do this in order to make sure that for soft real-time systems and hard real-time systems, we're still hitting our scheduled deadlines. And this helps keep everything much more efficient. So then, your drone has gone off, it's committed some war crimes, and now you want to verify if those, things actually happen, right? Did your mission actually succeed or not succeed? And so after you you get all these logs in your engine, you send it over to some like remote verifier that's going to verify if all of these things actually happen. And so this remote verifier is obviously going to verify the CFG for both intercompartments, so compartment to compartment talking, and an intra-compartment. So within a compartment, a critical compartment, for example, did things happen properly? Was the flow correct? But also we want to like verify the timing. And so this is something that's really important. If we log all the times, we obviously log the times between compartments, but within a compartment, if we log all the times, it's going to be way too much overhead. Like we get like 3.1 million control flow events per second in some of these really complex drones. So what we do is they propose re-execution. So on the remote verifying system, we actually re-execute the commands that we get from the logs, and then we verify the timing, and we can also verify integrity that way as well. And so this way you have like better performance on the system, but then you sacrifice, I guess, performance on the actual verification part. So going into the methodology, they ran a bunch of tests on different types of systems, complex systems, like rovers and drones and stuff like that, and then also like very simple systems like alarms and syringe pumps. And they measured the performance, the runtime overhead, and then certain policies. And so looking at the results, they were able to see that the runtime was actually and memory actually fit into like the proper proper segments that we actually needed. Runtime at the worst was less than 17% worse than like if you just ran it regularly, and memory took up 10% less RAM utilization than if you ran it normally. And we saw that actually for our scheduling, we were actually able to hit like hard real-time deadlines and soft real-time deadlines as well. But the big bottleneck here is this verification time. So verification time is taking 10 minutes per every 60-minute mission at its worst. The good thing is this obviously happens on a remote verifier, but even then, verifying that is a big thing. And this verification is batch process after every mission. Missions can consist of thousands of autonomous decisions, so you won't be able to stop like an autonomous decision from going on if it happens. So you might, hit the kid or bomb a car, but you only know afterwards. So the future work is that we can maybe improve the timing analysis. So re-execution, for example, that definitely is the thing that's taking a lot of time on verification. Maybe we can like parallelize this across like some like cloud workstation is what they proposed. Also for like have like estimating the timing of different like commands and stuff, we might want to use maybe some machine learning models like some decision tree or whatnot. We can also maybe combine this ARI with DAIT, which is a data integrity verification system that was proposed. And maybe also we can make like multimodal, so like have ARI work with like other sensors on the CPS to actually like determine if the system has its integrity. And do you guys have any ideas for any future works, perhaps?
Okay, moving on. Okay, discussion questions. So the first one is when scaling ARI to more complex CPS with a large number of components, what are some challenges that can happen? And how can future designs address these challenges? Any suggestions?
So I guess one thing to talk about, right, is like a large number of compartments is you're going to be having a lot more instrumentation added, because when you switch between compartments, you have, of course, there has to be some security checks that are going on. That's added by the compiler. So we get like a lot more like runtime overhead with a large number of compartments, and especially with a large number of critical compartments. So I guess going into that overhead, how can we address future designs or make policies? Like how do we actually determine what code goes into what compartment? Does anyone have any ideas behind like some maybe simple strategies that we could use to address that?
There's this thing called dynamic attestation, where it just like adjusts the level of like monitoring based on like the current state, so you can preserve resources. So that was the answer I had for that. Like, for example, if a system is in a low threat environment or under a heavy load, like attestation can be reduced. Okay, second question. Ari's approach only fully attests critical compartments of the CPS to prevent overhead, preserving real-time performance. Can you think of a scenario in which the attacker can exploit non-critical components to indirectly affect the integrity of critical operators?
Well, in your missile example, maybe you're saying that like some of these maybe like sensors might be like less critical, so you could just say that it's like detecting the target erroneously.
Yeah.
Right, exactly.
Okay,
And
so-
there was some talk as well about like I know I heard something in the news actually about like like drones being spoofed or whatever, like to like if you're dropping a bomb, for example, sorry, I use the bomb one a lot, but you're looking like the environment, and like maybe you have like maybe they falsify the environment or spoof the environment somehow, and then that's maybe checking the environment is non-critical, but the dropping of the bomb is actually critical, and that causes the bomb to drop prematurely. So ARI actually does have like checks on that, and those are the type of things I guess it's designed to actually like check with, especially with its re-execution and timing verification.
Yeah, so the example I used was, for example, like a drone, that just like flies it. Yeah, so if a drone's developers deem the sensor fusion model as a non-critical component, then attackers can use that because it isn't monitored as closely. So the sensor fusion module processes like sensor data so that the drone can kind of like get like knowledge about its environment, like for example, obstacles, just like yeah. So for example, the attacker can alter the altitude information so that the drone can fly like higher or lower than it normally would. Another example is it can try to like remove obstacles from the drone's path. Well, it can create the illusion that the drone doesn't have any obstacles, making the drone hit something. So
It's
yeah,
hard to kind of draw the line of what is sensitive and what
yeah,
is
exactly. It
critical.
ultimately just depends on like what the developers deem
Yeah.
as like critical and non-critical. Like you have to balance out the trade-offs
Right, and
between
they did a
the two.
user study as well in the paper, and they'd like actually like ask like some of the people in their like university to like make the policies for the compartments, right? So of course, with people who are more experienced with like CPS systems, they were able to realize like what was they should deem sensitive, non-sensitive, critical, non-critical. But like maybe some people who are less like in the security field, they would make sometimes wrong decisions. I think like generally they recommend that like you make the things that communicate with actuators, so like your bomb dropping mechanism, your like navigation systems, etc. Those would be maybe critical compartments, and maybe more like logic based stuff you would deem like non-critical, so you can catch errors when it hits the critical compartment specifically. I think one of the biggest problems with the paper, though, and I think they mentioned this too, was the fact that it's all batch process verified. So it is supposed to do continuous attestation. The problem is it's not stopping any event in real time. So I would say like the only problem with this paper is that like you're not actually stopping any events. You just know it. You're just doing like a post analysis of all of this.
Okay, question. Okay, I think that's it.
All right, thank you guys.
Thank you for listening.
This is group 3. When you're submitting your reviews, just make sure you don't switch.
Okay, hi everyone. My name's Tayu,
I'm Bharti.
and we're going to talk about Pistis, which is a trusted computing architecture for low-end embedded systems. So we'll talk about what that exactly means. So there are many system on a chips in the world, and many of them are in pretty mission critical systems. So we have a couple of examples of that, but there's like satellites, thermometers, sensors, and like server rooms, stuff like that. They're low end, so we don't really have the money to upgrade them, and they don't really have like certain hardware security guarantees that higher end SoCs would have. At the same time, we want to provide like security services for them. So remote attestation, secure code update. We mentioned remote attestation in class as well. Distance bounding, problems like that. How can we do all of this? How can we do all of these features and implement them in a secure way, even though we don't have any hardware guarantees? So how can we do all this just with software? So this is taken from the paper, but this is kind of an overview of like what the current landscape looks like for a secure computing architecture. Pistis is the very last row, but they made the major comparison to Sankis. And basically they talk about how a lot of these architectures so far they require hardware modification, which is the second column. Sometimes they are working with the Harvard memory model, which if you may recall, it has divides, there's a data section, sorry, and then there's also instruction section. So there's already a built-in memory isolation, which you don't get with von Neumann. Also, they don't support direct memory access and interrupts, which is kind of important for certain SoC rules. You kind of want interrupts like for mission critical systems. So we'll see how Pistis actually addresses these things. But first, again, what are these SoCs missing? They don't have like memory protection units. We can't really specify, okay, we are not going to touch this memory. And then we don't have those guarantees through hardware. And again, the von Neumann point that we had to somehow implement in software memory isolation without relying on hardware guarantees. These are just some examples of some SoCs, right? Security cameras, thermometers, and the last one is FPGA from satellite. These are all pretty mission critical depending on where they're used. So obviously we want to have security services. Cool. How do we do it? So we can do or how do we get these security guarantees? We can implement memory isolation with access control at runtime. And we'll see how that is done. But another further thing, actually going back to the first point, to be more specific, what that would look like is we have a certain trusted computing base that we say everything that runs in here is to be trusted, and then we have a certain untrusted section of memory. And then every time we want to actually download or we want to run some like application code, we can replace memory accesses in that untrusted code with virtual calls to our TCP. And then we can do those checks on where those accesses go to at runtime. And so this in theory should allow us to support DMA, interrupts, remote attestation, and secure code update. The last two will run inside our TCP. Yeah. This also ties into our lectures because we discussed how TCPs should be very small. They should be minimal, and they should, of course, be trusted, because without that, we cannot build our security services on top of it. Cool.
And this is pure software TCP. So
Yes, pure software TCP. Yeah. In the paper, they make a couple of slightly big assumptions. So one thing they say is no, they don't think about hardware attacks. I think their exact phrasing was something along the lines of like they think hardware attacks like are like orthogonal to the purposes of this paper, which is more about like on the software end, how can we protect against like malware, or like more specifically here, you can notice that the attacker can really only do like software attacks. Like we assume the attacker has access to anywhere in untrusted memory on this SoC. So they can eavesdrop, they can control any software, they can do all these funny little attacks in the last bullet point, but they cannot do hardware attacks. And Pistis, being all software, is not really able to defend against that in any way. Also no denial of service attacks, which is somewhat similar. And then we had to assume that the TCP or TCM is installed correctly. Right, that makes sense. Okay, cool.
Okay, so let's start talking about key contributions made by the authors in this paper. So this is the first and foremost, I think, concept where they're like using a pure software-based trusted computing architecture, which essentially provides security guarantees like remote attestation, secure code updates, and also memory isolation. And here they're ensuring that the memory isolation is entirely software, and it's like independent of the hardware, kind of hardware you're using. And it supports like direct memory access and interrupts securely, in the sense that, you know, the attacker cannot really bypass the security protections enforced by the trusted computing base. And the formally verified memory isolation design, as I alluded to it before, the root of trust is actually in software right now, not on some specialized hardware. And this another exciting thing about this is that it is portable to multiple similar low-end embedded devices, not just the one that they've used in this paper. And the authors released this as the compiler, basically as an open source C library, which uses like a GCC toolchain, and basically they kind of wanted to like automatically like enforce the secure code policies in the compiled binaries. So essentially, to talk about how does Pistis really work. So if you see here, the target platform used for this was the MSP 430 MCU, which is a very low power microcontroller. And as he already mentioned, it's based on one Newman architecture where you don't have like a different program and data space. And there's no hardware memory management unit or memory protection unit here. So the software components, the most important part obviously is the trusted computing module, which acts as the hypervisor here. It manages all access control. So essentially what happens is the trusted computing module is present in the flash memory. It's actually put into the flash memory by a trusted party like JTAG. And it replaces the bootloader code also to ensure that only verified applications can boot inside the TCM. And we have this loader verifier component, which is very, very crucial for this, because this is the only thing that the TCM trusts. It trusts, it ensures the authenticity and integrity of the instructions that want to execute here. And virtualized instructions, basically, the loader verifier can easily verify the static instructions, right? But what about the dynamic instructions? What about instructions whose addresses are not resolved at a load time? So those instructions, they are mapped into a subset of safe instructions via hypercalls, which are made to the TCM. So then thereafter, the TCM takes care of it. And interrupts are also handled securely. Like, I think they have two interrupt vector tables, and the ISRs, essentially they use addresses which are allowed or permissible for that particular access policy, whether it's read or write, etc. And we'll talk about the compiler toolchain in the next slide. Security services, in the image we can see that it supports remote attestation and secure code update. So remote attestation is essentially MAC based, right, as we've learned in class. So it essentially takes this whole memory state and computes a hash, and the verifier verifies it, and then if it's all fine, then yeah, it can be trusted. So the memory protection approach here, as I already mentioned, it's emulated in the software, no hardware. So it's divided into three different regions, like the protected zone, untrusted zone, which is self-explanatory. The TCM memory, you cannot read or you cannot write it. I mean, untrusted applications cannot read or write it. And we have this thing called secure storage, where sensitive data, right, they're stored in such a way that they cannot be accessed by untrusted applications. And if you see this image here, the attacker or the adversary can attack the tool chain in like different ways, right? Either a runtime attack or by injecting malware into the untrusted applications. So the defense against all of this, or how Pistis mitigates this, is by having this loader verifier inside the TCM. So even if the tool chain gets compromised, even if untrusted applications get loaded onto the toolchain, at the end, the verifier has to verify whether the instructions loaded or sent by the toolchain are proper, or like they adhere to the access policy. So this is essentially how the compiler toolchain works. So if you see here, there's something called as the instrumenter, which is used for rejecting unsafe instructions. So how do they determine unsafe or safe? Is they have defined some access policies based on which they define if these addresses, if an instruction which is supposed to like read or write, say an application data, it must follow some certain rules. If it's a control flow instruction, it must follow a certain rules, etc. And if it's a dynamic instruction, as I already said, it will map it to a subset of safe instructions that could be handled or resolved in the TCM at runtime. And there's something called as no-op slides, which is used for resolving dynamic control flow instructions. Basically, it's like a canary, right? Basically, to identify which are all the permissible locations where the instructions can jump to or branch to. And the link. Yeah,
Can I add something here?
yeah.
Yeah, sorry. So why we need to have that is because the paper was talking about how von Neumann architectures allow for variable length instruction sets. So you could essentially have an attacker if you didn't have something like the no-op slides, which like depend every instruction, then attackers could like jump to the middle of an instruction and like just run that, or run each as a separate instruction. Or make, yeah, they could do that, and then this is some form. This would be protected against via canaries, because then you define where instructions are, and you can only jump to those already valid instructions. Sorry. Yeah.
And the linker takes in something which is like additional modified memory layout, right? Now that we have Pistis, which implements these memory protection and memory isolation via software, we need a modified memory layout and not the actual memory layout. So the linker takes that in. And the loader verifier, I'd already explained that in the previous slides. It basically just verifies the instructions which are sent by the compiler toolchain, they are good enough. And this is an example of how they've shown this in the paper, how a dynamic call is being resolved. So here we can see that R10 is a register address. We don't know if it's like a permissible address yet or not. So what they essentially do is they convert that into a series of instructions here, and it gets mapped to this hypercall, like safe call instruction, which gets resolved in the TCM. So within the TCM routine, we can see that they just check whether this particular address is within some boundaries, right? If it exceeds that boundary, then we just do a soft reset. If everything seems good, then yeah, we can continue with the jump operation. And yeah, let's talk about how they evaluated it. So there are a number of concerns that might pop up, when you talk about evaluating this, especially the binary size, because this is supposed to be a low-end embedded device where the performance must not be like really achieving a great performance must not be like via a costly route, right? So here the binary size was found to increase by like about 41%. That is obvious because we are adding extra security checks. We are using these no-op slides, metadata, and they claim that despite this increase, it's still good enough for low-end MCUs because of the security guarantees it provides. And deployment overhead, yeah, as we can see here, the deployment time and the verification time, they significantly increase. But again, they think that it's justified because of the security benefits that come along with it. Then the runtime performance, they claim that it's dependent on the kind of application that we are running. So it shows like 13 different applications. They are both CPU intensive and IO intensive workloads. And so they found that the IO bound tasks, they have very low overhead as compared to CPU heavy tasks, which had like a very high overhead. So it depends on what kind of applications we want to run with the low end embedded device. And the battery life is again dependent on the application frequency. Worst case is when the battery life gets reduced by about 30%, where the frequency of execution is like really high. And best case is when we have a very negligible impact on battery life and the infrequent execution, basically.
Right.
Yeah,
So
very little time, so like finish it in like 1 minute.
1 minute. Okay. So we have, or they discuss like where they want to take their paper further. And first off is they only formally verified via some sort of mathematical proof that the memory isolation section, the implementation is safe. So it would be nice to see if they could extend that to the entire system. They also briefly mentioned that they want to implement control flow integrity. How this could happen on a low end SoC is very ambiguous, but pointer authentication, or that seems rather expensive. But also they only tested it on TI, Texas Instruments MSP 430. So if we could see this being done on other devices without customization, that would be nice. And like Bharti briefly mentioned, they said that the computation or memory overhead is not that much, because in certain applications like IO heavy applications, it doesn't really stand for much of total compute time. It would be nice if they said something nicer, like, oh, we would actually reduce compute time by doing these optimizations, instead of saying, oh, in these applications, it wouldn't be a big contributor anyways. And then we have some discussion questions.
I guess we can maybe just ask one of them and then we can pick your favorite.
The second one, it's like,
Yeah.
sure, okay, sure. Would integrating lightweight cryptographic accelerators like improve performance of business without violating the peer software approach? Would it improve performance a lot? Recall that there's only like what cryptographic things is business doing? It's doing remote attestation and security code update. Oh,
Yeah, I imagine, yeah, and it would improve performance a lot because it's like, very like resource constrained and like the cryptographic operations are super duper like how you have to like sign and like even patch it. Quite expensive.
yeah, we somewhat agree with that. Like we were talking about it too, and it really depends on like how often you're doing remote attestation. Like we were imagining in a low-end SSE, you're maybe doing that at most like once a day, potentially. Like and in that sense, it's not super beneficial. And how often are you running secure code update? I don't think so that often. The biggest security guarantees of Pistis come from memory isolation and like replacing the virtual calls, stuff like that. That's not done with cryptographic stuff at all. So yeah, but kind of. I think.
Alright.
Yeah.
Thank you, guys.
Thank you.
Generally, this is interesting when you don't have hardware, then you have to pay a lot of cost for software. Yes. Which is kind of the balance, right? So it works nicely with software only, but on the other hand, you have to pay a lot of penalty. Are you guys ready?
Yes.
Yeah, so hello everyone. Today's our presentation, 10 minutes presentation, will talk about the OAT, which is the testing operational integrity of the embedded devices. So let's take a look about the problems. Well, in nowadays, the rapid growth of the IoT has brought us a huge convenience. However, it's also introduced some like severe risks. For example, the embedded IoT nowadays are really vulnerable to some advanced attacks, such as the control flow hijacking, where attackers can take over the execution, and the data attacks, which just manipulate the critical data without like overtaking the execution. Well, these attacks will severely compromise the data functionality, which will lead to some like consequences about the data breachings or the infrastructure failures. So what is the real challenge for now is that the IoT backends have to blindly trust the data from the IoT devices because they do not have the ability to attack those attacks. And the gap in security is what the people want to address. So based on those problems, our researchers in this paper have like tell us a new method to address this gap, which called the OEI, Operational Execution Integrity. So this is a kind of security property which can be sent to the backend as a reference norm that can just determine whether the control flow have been altered or the critical data have been changed. So to apply the OEI, the others use a method which we may already familiar with, because this is from the lecture 11 called the two-player games. It's kind of a remote attestation method. And when operation runs, we can see that the IoT devices will acting as the prover and generates some unforgeable OEI measurements. It then sends this data to the verifier. In here is the IoT backends. So along with the operational result. So the backends will verify this measurement and only consider the data are credible if the OEI meets the security requirements. This guarantees that any action taken by the backend is based on the untapped execution. So unlike the traditional methods that will consider the entire program, the OEI will only consider a certain operation, which allows a more sufficient on-demand attestation without sacrificing too much security. However, it still have some problems and which will lead to another topic.
So in terms of current attestation methods, they are insufficient. On the one hand, control flow attestation methods like C-flat rely on control flow hashes to verify whether a program follows an expected execution path. But they suffer from path explosion, which means as program complexity increases, the number of possible execution paths grows exponentially, greatly increasing storage cost. On the other hand, existing methods lack data integrity verification. If an attacker modifies critical data like sensor readings without changing the control flow, these attacks remain undetected. To address these limitations, as mentioned before, OAT introduces OEI, which covers both control flow integrity and critical data integrity. For control flow integrity, OAT introduces a hybrid attestation approach. Forward control flow, like branches, is recorded with execution traces, while backward control flow, like return addresses, is verified with hashes to reduce storage cost. In this way, we can avoid the path explosion problem. For critical data integrity, OAT uses value-based checking, which monitors only critical variables so that we can reduce instrumentation overhead and improve efficiency. To be more specific, OAT consists of three key components: compiler-based instrumentation, measurement engine, and verification engine. Compiler-based instrumentation inserts additional instructions during compilation to track control flow and critical variables. Measurement engine runs with the ARM trust zone, which creates an isolated runtime environment, secure world, to protect the execution data from manipulation. Also, it generates an attestation blob for remote verification. Based on this attestation blob, verification engine can detect any integrity violations and reconstruct attack trajectories if necessary. And this is a full picture.
Okay, let's look at how they evaluate the systems. They tested OAT on ARM-based embedded devices, which are common in IoT systems. The evaluation focused on two main things: security and performance. For security, OAT successfully detected both control flow, hijacks, and data-only attacks. This is important because most existing methods cannot catch these advanced attacks. On the performance side, OAT only added a 2.73% runtime overhead and increased the binary size by 13%. This is really good because IoT devices have limited resources. The low overhead means OAT can work in real-world IoT systems without slowing them down too much. OAT's evaluation shows impressive results. It has only 2.7% runtime overhead on average, with verification taking just 1.89 seconds. Compared to trace-based CFI, OAT reduces control flow's trace size by 97.76%, and its value-based data integrity checking requires 74% less instrumentation than address-based methods. These results prove OAT is both secure and efficient for real-world IoT systems. Now let's talk about the key takeaways and future work. The main contribution of OAT is that it's the first method to remotely check both control flow and data integrity. This is a big deal because it lets IoT backends verify if devices are doing their jobs correctly. For example, if a robotic arm is hacked, OAT can detect if it has been manipulated. Current systems cannot do this. For future work, the authors want to extend OAT to support multi-threaded execution, which is common in more complex IoT systems. They are also looking into hardware acceleration to make the process faster and more efficient. Finally, I'd like to propose 3 discussion questions. How could OAT be used in other devices like smartphones or biometric systems? Could it help secure these devices in new ways? And what challenges might come up when extending OAT to support multi-threaded execution? For example, how would it handle many operations at the same time without adding too much overhead? And the third one, are there other types of attacks OAT could detect, like deepfake-based attacks on IoT systems?
You know answer for the third one? What do you think for the third?
We have a conclusion for that. It could potentially detect attacks that manipulate sensor data, such as deepfake-based attacks on IoT cameras or microphones. By verifying the integrity of data processing pipelines, OAT could identify anomalies in sensor inputs and outputs. For example, if an attacker attacker feeds fake video or audio data to an IoT device, OAT could flag inconsistencies in the data flow and help to prevent malicious actions based on manipulated inputs.
So you're kind of attesting the driver itself. Rather than,
This is kind of like the reference form aside with the output, so it
Yeah.
can, you know,
Yeah, you get the data, you also get the attestation of.
Yeah.
This one. Questions? All right, thank you guys.
thanks so much.
Thank you.
All right, guys.
Hi, everyone. We're doing one for all and all for one, a GNN based control flow attestation for
Maybe a
embedded
little bit louder
devices.
so that-
Okay.
My name is Vince.
My name is Alp.
And my name is Ryan.
So the prior arts and problem definition, the traditional control flow attestation methods include static attestation, which is hash-based, dynamic CFA, which is execution trace-based, and hardware-based attestation, which is a attestation mechanism that uses specialized hardware for runtime verification. And there are also machine learning-based CFA approaches, but they depend on precompiled data sets, require prior system state knowledge, and introduce a high computational overhead, which for IoT systems is not a viable option. And this paper aims to develop a lightweight GNN-based CFA system. So the key contributions include RAGE, which is a novel graph neural network-based CFA attestation mechanism. It is the first CFA approach to use variational graph autoencoders and detects control flow variations without requiring a complete CFG. It reduces computational overhead and can effectively detect ROP as well as DOP attacks. And it also exhibits a low false positive rate, and it was tested on mBench, OpenSSL, and as well as embedded software. So what is a control flow graph? A control flow graph is a graph representation of a program's execution flow. On the right hand corner, we see a complete CFG of a basic program, and right below it, we see a partial CFG, which includes inferences for possible execution paths. CFG completeness is a NP-hard problem due to indirect jumps, dynamic function calls, as well as programs containing too many execution possibilities. So CFA, what is CFA? It is a security technique that is used to verify a program if a program executes exactly as intended without any malicious modifications. It detects unauthorized modifications to a program's control flow, specifically code reuse attacks. A verifier checks the integrity of the execution on a prover, which is an untrusted remote system. But the limitations of CFA are as follows. So one, it requires complete CFGs. It cannot detect runtime attacks, and hardware-based attestation is costly and unavailable in embedded systems. That's why RAGE introduces a lightweight system that is applicable to embedded systems. Code reuse attacks pretty much reuse existing code in memory to complete their attack. There are three types, which is return-oriented programming, jump-oriented programming, as well as date-oriented programming. These cannot be detected by signature-based systems and also appear as legitimate execution flow and partial CFGs. And this is where the graph neural networks come into play. Traditional neural networks work with structured grid-like data, including images and sequences, while GNNs work with graph-structured data where information is stored in nodes as well as edges. And they're able to capture complex relationship and dependencies in structured data. And why they're preferable? Because they can learn from a benign execution trace and generalize attacks. They capture both local and global execution flow anomalies, and they don't require large data sets for benign or malicious traces. And RAGE is a graph neural network based, as well as variational graph autoencoder based system that is explored in the paper, and it learns execution embeddings from a benign trace. So it has two phases, the training as well as the attestation phase. And it compares new traces to detect deviations without, again, requiring a full CFG, which is NP-hard. So why is this significant? It works on incomplete control flow graphs, and it exhibits unsupervised learning with no labeled attacks needed, and is also computationally lightweight and suitable for deployment in embedded devices.
So jumping into the RAGE system level design, we see two phases, the training phase and the attestation phase. The training phase consists of the prover collecting a set of benign traces, the verifier then pre-processing those into a partial control flow graph, and then using that to train their VGAE model. Additionally, the embeddings within these graphs are extracted to calibrate the attestation threshold. The attestation phase is when we have a trace of code that actually wants to be attested for, where the prover traces one execution, preprocessing occurs, the verifier extracts the embeddings from that graph, and then distance computation between executions is calculated, essentially how different or similar or dissimilar those two graphs are. After that, the attestation outcome is determined based on whether that difference is above the attestation threshold or below. So geometric deep learning in RAGE. Why do we use geometric deep learning? The reason why is because it extends deep learning to non-Euclidean data, for example, these graph structures. That's important because the execution traces can be represented as graphs, and the complex relationships and notions of distance are preserved when these are represented as graphs. GDL-based RAGE learns execution patterns directly from the execution graphs, then generalizes those to unseen attack patterns as well, and it can detect both control data and non-control data attacks. So attestation threshold calculation, how the attestation threshold is actually calculated is one known benign trace trains the VGAE model, and then 10 other random traces are taken from the validation set, and the distances between those and the initial benign trace are calculated, then the mean is calculated and the standard deviation is as well. And the attestation threshold then becomes 2 standard deviations away from the mean. And this method ensures efficiency and a low false positive rate. So for the experimental procedure and results, RAGE was evaluated on mbench, OpenSSL, Diffie-Hellman, key exchange, and other datasets as well. The main metrics of evaluation that we care about are F1 score, which we can see here is kind of a mix of precision and recall, and false positive rate as well. And as we can see by the statistics, the F1 score for all 3 of these was quite high, actually, with mbench even going above 98%, which is pretty good, with low false positive rates across the board as well. And we do notice, though, that RAGE is better at detecting ROP attacks than DOP attacks. The reason why is because ROP attacks directly modify the control flow graph structure, whereas DOP attacks do not. So ROP attacks are a bit more obvious in that sense. Speaking about the performance and overhead, RAGE has a low computational overhead, thus making it feasible for embedded systems, and only one trace is needed for training, which is great because it reduces storage and computation requirements. We actually find that the embeddings from the graphs give us all the information we really need. RAGE effectively also detects both ROP and DOP attacks, which is great because the current state-of-the-art BLAST, which builds upon OAT, only detects ROP attacks, not DOP, and requires access to the complete control flow graph. So we see that RAGE has made several improvements in this way.
So now we're going to talk about 2 security considerations when using the RAGE model. The first one we're going to talk about is the implications of not assuming completeness of the CFG. So the traditional systems we've talked about, they rely on complete CFGs. The RAGE model does not. It only relies on one single execution trace. It's able to learn the program's benign behavior, and it maps high-dimensional data to low-dimensional spaces. What does this mean? It means that it only requires basic block addresses, and it's helpful because it prevents any information leakage to the verifier, and it helps reduce overhead and complexity. The second consideration has to do with CRA detection. So attackers, they will reuse existing execution paths and make it hard to detect. However, the RAGE model, it does have a high degree of accuracy when it comes to detection. It extracts low-dimensional embeddings and uses probability sampling so that it can output distance values when comparing malicious and benign executions. For non-controlled data attacks, the RAGE model will also output distance values by using features from the execution flow with a potentially compromised execution. So speaking on the related work, the three methods from the traditional methods include static, control flow, and machine learning based attestations. And the RAGE model is different in that it's the only CRA scheme that utilizes graph neural networks. It exploits the correspondences between execution traces, graphs, and embeddings, and it's able to perform attestation of the full software just by analyzing the benign execution behavior. So how is this applicable to the real world? We've found a couple fields that it could be used in, which include industrial IoT security, medical device security, automotive cybersecurity, and financial and cryptographic systems. So the unique properties of the RAGE model, differing from traditional methods, we could see it as potentially being useful in improving attestation for these fields. We do have some critiques, and we're going to talk about future prospects. So speaking on the strengths of the RAGE model, it's efficient. It has high detection accuracy. It's unique in that it doesn't require a complete CFG like traditional methods. But it does have limitations in that in the paper, it was only tested on embedded benchmarks. It hasn't been tested on real-world deployment, and we could see this as potentially being explored in the future. Another thing is its dependence on the quality of the execution graphs. So relying on one benign execution trace may lead the model to behave in such a way that it doesn't cover all normal variations, and it might negatively impact the detection of malicious traces. So speaking on discussion points, we have 3 below. So how does the RAGE model compare with traditional CFA methods in terms of advantages and disadvantages? Why are DOP attacks harder to detect than ROP attacks using the RAGE model? And what are the implications of using a single benign execution trace to perform RAGE?
The second bullet could be a good quiz question, actually.
I was thinking about the third one, I was thinking about code coverage, like you have multiple very different paths in your program, but if you only use one trace, then you might not be covering most of it. And you'll just your model will say the other ones are just sus because they're too different.
We agree. Yes.
Let's take the third one, maybe the one, usually your system has input data from the real world, and if it doesn't match the input that you gave during your benign execution, then it's likely the model will be trained incorrectly, because you probably can't predict always what's going to come out from your real world, and if something comes in that's strange but still interesting, it might affect your control flow, which messes up.
That's a classic coverage problem that we always see. Fixes. Okay. So why DOP is more harder than ROP? Detecting DOP is harder than ROP. So could be your quiz question.
Yeah, I think from the presentation, they said return programming qualifies the control flow graph. So obviously it's gonna be much easier detected, whereas DOP doesn't modify control flow graph. Yeah, I think probably DOP includes traces and stuff, maybe the data flow graph.
Yeah, exactly. So DOP doesn't create new edges, versus ROP create new edges. So by just looking at new edges, you cannot detect them.
Speaking on that a little bit more, there are some methods to detect DOP that kind of involve how often a certain node is visited, how many edges go into a certain node, how many times, and stuff like that. So it's detectable, but it's not as good.
Yeah, good point. All right, thank you guys.
Thank you.
So we are group 6 and we are presenting Shift, the semi-hosted first testing for embedded applications.
First, let's talk about problems. As we talk about the dynamic analysis in the firmware, we always feel some challenges like the low fidelity and limited capability. This may cause missed critical bugs. They may hide in your code or somewhere. It's very hard to find or fixed sum. And in this paper, we propose a new way called shift. It's a novel rehosting approach, and we call it semi-hosting. It's like a framework, and basically what we done is we run the entire fuzzy infrastructures and the target firmware directly on the MCU, while we still keep the generation of the fuzzy input on the remote workstation. Like we decouple them and separate them into two parts. First, here, as we talk about the firmware analysis, we talk about the dynamic analysis, which mentioned in the Model 7, and it's a good way, but the dynamic analysis always face the problem of the incapability. I mean, yes, all these existing security tools and methods we use for the general coding, it always suffer from incapability with unique working conditions and constrictions of the firmware running on MCU. This is because embedded devices has its own characteristics, and we can't just ignore them and doing what we want. So the rehosting technique also mentioned in the Model 7, it's a mainstream technique we use. Basically, we run the binary that used to run on the MCU, and now we run them instead on the remote workstations. It's something like emulation, and the different kinds of it. But they are faced with the basically same limitation, like the fidelity and the observability, also the limited capability. Because we are doing emulation as approximation, we must do something to make it.
Okay, so the solution, kind of like what was mentioned before, is Shift, which is a semi-hosting technique where the MCU firmware, like we said, runs natively on the actual hardware, but the fuzzing capabilities are from more of a remote workstation. And then the two can communicate via USB serial connection. So instead of the formerly tried rehosting techniques, this one kind of leverages the best of both worlds, something on the hardware, some software emulation as well. So some of the specifics is that it uses that semi-hosting technique, but more importantly, it's vendor agnostic. So they were able to make it support multiple MCU architectures across many of the most popular ones, from ARMv7, 8, Extensa, and 13 other popular architectures. So this really increases the compatibility, which was an issue from the methods that were tried before. Also, it does eliminate software emulation due to non-reliance on the emulating hardware. It supports instrument-based bug detection, like address sanitizer and coverage sanitizer, and supports single and dual core configurations. And it also includes fault detection for timeouts, memory errors, and
So how do we evaluate the performance of this strategy? Well, so the first thing we do is like they tested shift compatibility by running it on certain popular embedded architecture. So both kind of RAM and flash memory usage was measured, so we can make sure that it can run on even like resource constrained device. And also the synthetic benchmark were used to where we like deliberately inject errors into the system, some like memory faults, division by zero, and some common bugs. Kind of like an exam where we kind of grade against like an existing answer to see if it performed as expected. And also we compare the hardware native execution against the emulation methods so that we can understand its fidelity and performance. And lastly, we use case study to make sure we can actually run it in the actual real world setting instead of like a lab setting. Because it's like kind of easy to get pretty data from a lab setting, but if you want to make sure it runs in real device, you need to put in some solid work. And for the result looks pretty. The shift runs up to 100 times faster than software-based emulation, and it's even comparable to the native fuzz testing on workstation. Importantly, it uncovered 5 previously unknown vulnerabilities, including a 0-day bug in the system. So this is kind of impressive because it kind of tells us this system can actually handle with the real world situation. So it's not like only good on like some problem that already has like existing solutions. And also it has no false positives. All issue detected were actually confirmed. And the framework also shows high fidelity, accurately capturing complex interactions such as DMA operation and peripheral communication. And a small problem with this method is, of course, since it's like a hardware solution, it cannot scale as those like a software emulation because you cannot just like click install and problem solved. The hardware is something that we need to actually implement on every single device, so it's not as scalable as the software one. But as a trade-off, it's more reliable and run faster. And for some of the use case, well, it can be applied to various areas. So it's particularly useful for early stage security testing in IoT and embedded device, where catching like firmware vulnerability early can prevent major issues in like smart homes, connected vehicles, and industrial systems. These are the places you don't want to fix it after things happen. So you need actually to catch it before things went wrong. And also it can be integrated into continuous integration and delivery pipeline, ensuring ongoing security validation during the development. Lastly, by reducing the false positive, Shift can complement traditional testing method and help developer focus on like real critical vulnerabilities.
So now talking about what kind of the future could look like for Shift, one of the main problems with it that we touched on a little bit, but it's very focused on binary only firmware. So that means that like people that created the products, like they can test it the best because they have access to the source code. But we want it to be able to be tested by like third-party testers and like be able to mass test like different products. So not just the people that created it, right? And so that's like one main problem is that you can't really use Shift without access to this source code, which is really important. We also want to be able to use the semi-hosting concept, which is like so unique to Shift, to other security analysis techniques, like for example, concurrent execution. So like this one, concurrent execution is like more powerful than just what Shift test is because it's able to use like different computations to actually test the algorithms and math behind the code. And so we want to be able to use semi-hosting for that because it's very computationally expensive. And so semi-hosting can help with that. And then one other problem is that like Shift uses a lot of RAM. It can use up to like 23% of RAM on like some of these MCU devices. And so because of that, if there's a way to like make it a little bit more hardware efficient, then we can use it on more IoT devices. So conclusion, like based on everything we've talked about, is that it's considered complement like a in addition to like the current software approaches that we have for emulation, but it can't be just used as a replacement because it's not able to scale properly right now, and it can only be used for a certain number of devices. There's a lot of like different compatibility errors with it, and but it is very powerful for security researchers, and it has a lot of potential, especially like industrial automation, obviously IoT device security, and also automotive cybersecurity. So based on everything we've talked about, like we have a few questions for you guys. One would be like, how does Shift compare to emulation hardware in loop in terms of testing accuracy and speed? Another one is like what challenges might occur when adding Shift into existing firmware development, especially on low resource devices or when secure code is not available. And then lastly, how can Shift be improved to work with new embedded architectures and other testing techniques?
Well, I mean, Shift's kind of like balance between the two, right? So it does a little bit of emulation, a little bit of hardware, which is good. But the whole problem with this balancing between the two is that I also don't get the good things from either as well. So yeah, so it's kind of both good and bad. So, what do you think about the second question? Like, did they talk about not having the source code and how do you instrument the binary?
They didn't really talk about what happens if you don't have the source code, but they did say that it like in conclusion, they said that there's like more potential with like a little bit more testing that if third party like can be able to like integrate with it properly.
Any questions? Good. All right, thank you guys.
I'm Renika.
And today we'll be presenting about RealSWOT, remote software-based attestation for embedded devices under real-time constraints. So the focus of this paper is basically to answer this question. How can we securely verify the integrity of software running on a real-time embedded device without introducing any delays or requiring specialized hardware? And this is an interesting problem because real-time devices, like mentioned in by the first group earlier, they have to meet precise timing requirements or they may behave unpredictably. So let's consider the diagram over there showing the basic attestation process where a verifier sends a prover a challenge and they have to compute some kind of hash before sending a response. This execution overhead may lead to the real-time device not being able to meet its real-time like demands. And if we do respect the real-time demands of the system, this could lead to the talk to problem that we talked about in class, where the adversary is able to sort of revert the state to the benign state during the attestation process, and then after attestation is done, revert back to malicious code. The third point is not technical, but I think it's important for us engineers to understand is that it requires costly recertification of real-time devices, especially in domains that are safety critical like aviation and healthcare. So let's quickly go through the threat and system model. The tested device is a ESP32 that runs a real-time operating system and has strict timing constraints and cannot be interrupted. So what's important is that this system, this device has multiple processor cores on it, and one processor core is dedicated just for attestation. And this attacker has full control over the device. And the prover, this device, which is the prover, exists within an IoT network and can communicate with the verifier. And this network is prone to jitter, so the attestation process must be resilient to unpredictable transmission times. And lastly, there's a trusted IoT gateway that ensures that the prover cannot offload attestation computations to a computer outside of the network, and no unauthorized devices can join this network.
So here's the proposed solution is RealSWOT, which basically is just real-time SWOT. SWOT is software attestation. So I just wanted to recall some key points about software attestation. First is that there's strict timing assumptions about the response of the prover from the verifier. So this is important because it asserts the integrity of the measurement process. And yeah, this is so important because it like demands all system resources. So it makes sure that like an attacker cannot like use system resources for something else during like the attestation process, like the measurement process. Yeah. So in this paper, there are like two main points of innovation that they talked about. So the first one was just to use a separate processor core to do all of the attestation work. Right. And this kind of like I'll talk about it later. And also the other point is that it uses continuous attestation to mitigate problems such as like talk to or like false positives due to like transmission delay. So why does it use a separate processor core? As Pierce talked about, in RTOS systems, it's real time. So it's very important that tasks are completed in real time and on time, right? So a separate processor core allows it allows the system to continue completing its task while attestation is performed on another core. And as I said, there's continuous attestation being performed. So as a result, we have to like offload it to a separate process core. Otherwise, it's gonna like take up a constant resources on like the main core. Yeah. And she just says why you should not give like the RTOS scheduler priority, right, over attestation directly, because this could be misused by an adversary to like do other things while we're doing attestation, right? So that and so this we will have to accommodate for like the worst case scenario, and so our timing constraints will not be very accurate to perform attestation. All right, so the paper also introduces continuous attestation, and so like there's like two main concepts that I think arise from this. So the first is that because of continuous attestation, the verifier can safely assume that at all times this separate processor call is like doing the attestation, right? Because otherwise the timing checks will fail. And the attestation scheme, according to the paper, is independent of transmission between the prover and verifier under the assumption that the transmission time is significantly smaller than the time required for the attestation. So like this didn't really make sense to me, like because like isn't like the transmission time part of like the time that like the timing check, right? But I'll talk a little bit about like what the paper means by this in a bit. So first I'm going to talk about like how the continuous attestation is implemented. And so the main thing is that the hash function must not be parallelizable. Otherwise, like the attacker could use like other cores within the system to speed up the hashing process such that it can do something else with the attestation like core in between. So this is not what we want. And another point is that because this is like a continuous attestation process, the next nonce will be sent just before the next measurement should start, right? So this prevents the attacker from like starting on the next attestation like before like the previous one has been like concluded, right? And so like the hashing method will take the hash from both like the previous hashing as well as from the nonce from the verifier, so that it's like it cannot just like start by itself, before the verifier has sent the nonce. All right, so this is the main point I was a little confused about, where like the paper says that like continuous attestation omits the transmission and verification time. But what like the paper is actually talking about is that like in normal software attestation, once like the prover is done with his hashing, he has to like send the resulting hash and then wait for the new nonce, right? But with this continuous attestation framework, there's no gap between the prover because the next nonce like arrives before like the computation is finished. So like, oh, sorry. Back to like this. Oh, wait, this is. Okay. Yeah, so like this is just the diagram of how it works, right? So like the nonce comes in, and like the second nonce is supposed to reach like the prover before like it's done with the hash. So that like this attestation will like keep on going, and like the core doesn't have any like free resources to like perform anything else. So that's like the main concept. Yeah. So this is what the paper means by this like omits the transmission and verification time. So it doesn't mean that like the check like doesn't include the transmission time. It does. It's just like this just the attestation is continuous on that call.
There is an overlap, right? You hide the latency of the network while you're doing the call.
Yeah, that's basically what. So my explanation is not very good. Okay, other thoughts.
That was good.
Yeah. So in my opinion, like continuous attestation is quite useful. It's always like monitoring the device state. So as I said, like the separate processor core can't like go and do other things in this period of time, otherwise you will fail the timing checks, right? And additionally, I was like thinking about it, but like because the attestation is being done continuously, you can also like average the time taken over a few attestation cycles, right? Because like as we talked about a problem in class is that the transmission time due to network latency can vary quite a bit, right? So we don't want to just like take a single time usually. We might want to take like an average of like the time so that the verification time, so that if there's like only if there's a significant increase in the average, then we know that probably the core has been used for like something else during the verification process. Okay, yeah. All right, so I'm just gonna quickly talk about some upsides of real SWOT. So like this, for example, simulates applying the NX bit. The NX bit means that like a piece of memory that is like writable cannot be executable. So it kind of like implements that, like simulates that on embedded systems. And as I was saying, continuous attestation allows for continuous validation. And even though like the attacker may so-called be able to like copy memory around like very quickly and try to execute it, like that's like very difficult and also extremely time consuming. So this like continuous attestation process is actually quite secure, and it may even deter the attacker from like attempting an attack, even if the verifier is not actively verifying the prover's measurement, just because of like the scheme being like very, very like secure. Right, and in terms of functional upsides, yeah, it's suitable for RTOS because it only occupies like a separate unused core. In terms of security limitations, the first one is that it's similar to what I said earlier, like the code could technically move between like memory areas that are not being like hashed or verified right now. But at the same time, I do have to say that like it's a little like it's not that easy to like accomplish because of the cost of it. And other than that, we also cannot verify the entire RTOS because like hashing needs to be used with care because it limits the state representation of the software, right? And like there's definitely needs to be some areas of memory that's like volatile and used for like temporary variables, right? So if there's sufficient unverified state representation, like attackers could use that for their like malicious code. And last one, this is already addressed by the paper, but if like attackers could technically offload hash computation so that like they could do something else on like a separate like a delegated like server and instead of doing it on like the separate core, but this is mitigated by the IoT gateway that Piers talked about earlier. Okay, and lastly, the last limitation I'm talking about is like the cost. So this is like very costly because like it's continuous, so it's always happening. And you think about like what happens on the verifier, right? On the verifier side, because like this needs to happen like one after another. So it means that like for every prover that is like trying to prove, it needs to like run its own like chain of like hashing with the nonce as well. And so like this is like basically very like costly in terms of like for like power, memory, and everything. And like you need to continuously talk, so that's also like strains the bandwidth budget. Oh yeah, and then the last part is just the technical details of the implementation for the paper. We just use like ESP32, which has 2 cores for like concurrent processing. The verifier is a Raspberry Pi on Linux. The network, they use UDP packets, so that it's like less overhead from like the TCP handshake and stuff. And then the IoT gateway is basically that. And yeah, I'll let Mark go through the results of the paper.
Good job. Yeah, so talking about the evaluation methods, they kind of looked at 4 main things, and TS has talked a little bit about some of them. So for the main thing that they wanted to evaluate was the timing. So when you have the hashing function for your attestation, you don't necessarily only need to hash once. You can hash multiple times, and that will allow you to change how much because when you send to the verifier is expecting it within a time window for your attestation. And the more repetitions you have your hashing, the less percentage-wise the network latency of sending to the verifier is going to impact your window of like when the attestation arrives, which gives less time for the attacker to do anything. They for Wi-Fi, so they had 2 different testings that they did. They did for every different like amount of repetitions of the hashing, when they did the transmission over Wi-Fi, they did 600 measurements. Because the network had variability, they wanted to have a lot more measurements for that. They found, you'll see later, that when they did the measurements directly on the device, on the real-time operating system, that the variance was much lower, sort of obviously, and so they did much less measurement for that. Beyond that, they wanted to see how much extra power that the IoT device would need to run this continuous attestation. They wanted to see the communication overhead. And they also just wanted to understand, like, is this actually feasible on a real device? And so talking more about timing, you can see this is the table from the paper where they have different rounds of hashing that they do like per attestation. And you can see that for the network ones, there's a much higher standard deviation than the direct ones, which again, just is due to like network variability, which means that you would want a higher, or you would want more rounds of hashing for your attestation because that helps you lower the standard deviation for your attestation, which allows you to make the window smaller, which allows you to limit the amount of time that the attacker can do stuff that you aren't seeing. The problem with increasing the rounds of hashing is that every round is time that the prover has to spend, and that means that like your time to detection increases just sort of by the nature of doing more work. Yeah.
Just curious, the standard deviation seemed to like be all over the place until you get to like 100. Did they have any explanation for that?
I didn't see any explanation for it.
Big low and then jumps up high and then jumps back low.
Oh yeah, it's direct versus network.
Well, no,
So-
if you only look at the network ones.
Yeah, so they didn't give a full explanation. I was kind of confused why like with like the 0 rounds and the like all right, more specifically the 20 rounds one really kind of confused me because it just sort of like shoots up. And they never address this in the paper. And like I don't know. I was very confused about like why the 20 rounds one was like so terrible.
I think, wasn't it because there was like probably few of these attestations that were like really high latency and they happen to be under 20 and then they kind of averaged out as they move up. Right?
Yeah, I mean,
so if let's say for example I've run it 20 times, the first 10 times is good, there's not much variation, but there's like two faulty ones, like I don't know, like 12 and 13, big jumps.
well, so these are the rounds of hashing. So for each set of these rounds of hashing, they're doing the same number of attestations. So for the network ones, they do 600.
So for the network one, what is causing this deviation is the latency of the network, right?
Yeah.
So I send a message, I wait, I receive something. What I'm saying is that probably in one of these rounds of attestation, there has been a huge network delay because of maybe some congestion, some
Right.
other issues. That's why the standard deviation.
I would assume so, because like you said, the only real way that you would get such a jump is through network like variance, but they never address this in the paper at all. But yeah, one would assume that like it's just based on like the network variance. And so this is one of the things I kind of want to talk about. Like if you wanted to do this on your own devices, you would probably want to like measure this on your network, like and do the testing for it and do it like a lot of times because like their network is not necessarily representative of your network. And so like they kind of in the paper were like, yeah, you can just use this table to figure out like what you want. And I wasn't super convinced because networks aren't just like easily copyable. But yeah, so in essence, if you wanted to implement something like this, you would kind of make your own table like this from testing, and then you would balance like, okay, how often do I want to do my attestation versus how much like precision do I want, or how much do I want to limit the attacker's window of doing things? And this is like a balance that you just make for your device, right? So with the syringe, I think I didn't mention this, but for the evaluation, they use a syringe pump, which they implemented it on. So the paper for their conditions selected 5 rounds of hashing for direct verification because you get like perfect precision and you limit the amount of like rounds you need to do, whereas it selects 100 rounds for the network based, which gives you verification about every second, which for a syringe pump is good enough.
We don't have much time, so maybe we want to go to the end of it so that you can also.
Okay. This is all fast. Basically, all of this is just saying that like the power consumption doesn't change much. The communication isn't like a problem. Implementation, there's a few weird things you need to think about, but mostly it works just fine. And
Okay, so for future potential works, RealSWAT is not ideal for all IoT devices because many IoT devices cannot afford the cost. For example, if a device only has one core or cannot afford to like specifically use a core just for attestation. So some ideas are having time slice attestation, which breaks like the process into smaller chunks, or hardware protection to reduce the risk of talk to attacks. And this might not be feasible for legacy devices if the specific hardware is not available. And for discussion, this question was kind of addressed, but what can be done to verify that attackers cannot offload hash computations to a more powerful machine?
Isn't the continuous fix this issue? I think that's their main thing, right? So they don't have free time to upload it to anywhere else. I think.
I think part of it is also like the IoT gateway that Pierce was talking about. Like if you everything is routed through the IoT gateway, then you can like detect malicious like
that's also
behavior.
Yeah. So the idea was like an IoT gateway can be used to detect like problematic behavior. Okay, and another question is previously we stated that if there's sufficient unverified state representation, attackers could place malware in memory. And what is one way we can prevent this?
Also good quiz question.
Okay. So
One way we can verify that attackers cannot place malware in memory is using memory protection units or MPUs to make sure that only certain sections of memory can be executed. And another thing we can do is use some sort of control flow integrity mechanism in the hardware to ensure that only verified code is executed.
Or not having any unverified state, right? Like if you check everything, then you should be good. All right, thank you guys. Appreciate it.
Thank you.
All right, let's conclude the presentations. Thanks, everyone, and see you guys on Wednesday.
Actually, not a one. Also noted.